There is some redundancy with talks that may have happened before in this meeting. I also should confess that it's a little bit ironic to be doing this in recent trends. Some of the stuff goes back to the 50s, so hopefully we'll work our way up to something that might actually qualify as reasonably recent. We'll see. I'm going to introduce the standard voting setup and the kind of problems that people typically like to ask in this setting. And then we will move on to restricted domains, and I will have a brief sales pitch for why these are interesting constructs to look at. We'll also talk about making these notions a little more interesting for real-world problems, and finally a heads up about things to watch out for as you think more about the notion of restricted domains. And I should say that this can more or less be treated as the first part of a two-part talk, so Kailash will have a lot more to say about problems of different flavors, but I believe he will also be talking a little bit about restricted domains in that context. So yeah. So the standard setup is that, so again, I'm going to be limiting myself to a largely computational take on these problems. I should say that there is a very large body of work that looks at these things from a more axiomatic perspective. And I briefly mentioned the goals of that perspective, but it's something that we will not be getting into in any kind of detail. But the setting is that we have a bunch of candidates or alternatives. So you can imagine a group of 4 friends, maybe, or a few friends, and you're trying to figure out what to do after all the talks are done today, relax in the evening, maybe. I don't know if there's like a football match going on or a concert, but let's just believe that there are these options that exist for you. And of course, people have preferences, and there are different ways in which you might want for people to express their preferences. The most natural is perhaps just asking for a ranking, what's the thing that you want to do the most, and what's your next favorite option, and so on, all the way down to what's your least favorite option. So that would be, so maybe somebody prefers to have coffee, quiet cup of coffee, over going to a concert, over maybe dining out, over the football game, and so on and so forth, right? So these are rankings over the alternatives. You could also ask instead for the so-called approval ballots, which is to say you do a thumbs up or a thumbs down on each of these alternatives. I'm willing to do this and I'm not willing to do this. So this is a much coarser way of asking for preferences. Rankings are typically a lot more work because you are, you're actually making a list and you have to think about this quite a bit. There are yet other models where you may ask for people to give a number. So in fact, even in the case of rankings, it may be that 2 people have the exact same ranking over the alternatives, but they feel more strongly about how far apart the alternatives are. So some people like to model this using, I guess that would be the cardinal setting, where you actually have numbers. And there's all kinds of intermediate ways in which you could ask for partial orders, and there are many ways of modeling preferences. We will keep it relatively simple when we look at rankings, and I think Kailash will have more to say about the issue of rankings being hard to select. So maybe you want to be able to infer somebody's ranking by asking only a few questions. And since that's going to be the subject of the next talk, I will not delve on that, but instead, let me just define a few basic notions. The first one is of a social choice function, where the idea is that we're given a bunch of rankings as input, and the goal is to hopefully come up with some sort of a winning alternative. It's a natural goal. You folks want to probably figure out what you want to do this evening. So what is an alternative that, depending on how you look at it, if you're an optimist, you will say make everybody happy. If you're a pessimist, you will say, well, it doesn't make anybody too unhappy. So that could be one sort of a goal. You might also be interested in coming up with a ranking over all the alternatives that is the most true to the overall preferences of the sort of society that's engaging in this exercise. You may also want to, so here this is an ordered list, and you may also want to select a subset of activities. Maybe this is a 4-day workshop, so when there are only 4 alternatives, so maybe you can do something different every day. But imagine that this was a 2-day workshop and you had to pick just 2 options, which would be the best subset to pick. Airline industries definitely have to make a choice of what films to show on their entertainment panel, and they actually run these multi-winner sort of processes to figure out what subset of alternatives to pick. So this is sometimes called the committee selection problem, which is a multi-winner voting rule and so on. I'm skipping a few nuances in the interest of time. Your mechanism in this case, skipping over the issue of what might happen if you have alternatives which are both equally good from the perspective of the mechanism. So you may have ties, and you may have to worry about tie breaking. I'm kind of brushing such details under the carpet. At a high level, the usual problems that we're interested in, as we just said, is this notion of a best alternative, or what is a ranking that captures the sort of the vibe of the society, given all these rankings as input. You might also be interested in more, if you like, game theoretic issues, like, for instance, do the agents who are involved have an incentive to cheat? Do they get a better outcome from the mechanism that's trying to figure out the best alternative or the best ranking or the best committee by misreporting their preferences? So I don't give you my truthful preference, I give you something else, and maybe you give me something that I actually prefer more. And that could actually turn out to be an issue, so a lot of people look at this as well. And along similar lines, this is a little more violent, I suppose, but does the removal of a candidate affect the outcome of what is going on here, right? So this, or does the removal of some votes affect the outcome? So as the duplication of candidates affect the outcome. So we've seen all these things come up in the news. If you think of this as a traditional election setting, I don't know about candidates getting knocked off, but certainly ballot boxes get nicked, and we had instances where fake or fraudulent parties were added to the ballot to make it look like, to create confusion among the voters about whom they're actually voting for. So these are all fairly real issues that you could worry about. So roughly speaking, this is the winner determination problem, where you can come up with several ways of choosing an alternative. And the axiomatic perspective of this issue would be to say that if you give me a method to pick out a best alternative from a bunch of rankings, then this method should satisfy certain desirable natural properties, like, for instance, unanimity. If everybody prefers a candidate at the top spot, then your mechanism should hopefully report that candidate as the winning candidate. So that's a pretty sensible property to demand from a mechanism. And there are many such natural sounding properties that you might want your mechanism to satisfy. And the axiomatic folks like to say, let's say property P1, P2, and P3, what are the kind of voting rules or what are the kind of choice functions that satisfy the properties P1, P2, P3. Depending on what those properties are, these combinations are usually very desirable. But the field tends to be a little depressing because it's full of so-called impossibility results. So most theorems are along the lines there is no mechanism that satisfies these nice properties that you would obviously want, unless it is something like a dictatorship, which is a mechanism that you don't want. I'm not going to formally define a dictatorship, but you probably already know what it is, right? So that's the sort of thing we won't be looking at. We're just going to be looking at some examples of voting rules that are already sort of proposed in the literature or are being actively used in practice, and we're going to ask ourselves more questions with a more computational flavor. Okay? Similarly, coming up with a ranking rather than a single winning candidate, sometimes called reference aggregation. This problem of voters deliberately cheating about their preferences is usually referred to as manipulation. Issues like this go under the broad theme of control. So these are just keywords in case you want to look up some of these things. But we will focus by and large on the winner determination problem and maybe a little bit about manipulation as we go along. So let's just make this a little bit concrete and look at some examples of choice functions, an example of a multi-winner rule and an aggregation function. Are there any questions so far? Is there anything about the setup that is not clear or anything else? Okay, I will go on. The most natural voting rule is perhaps plurality. So let's say that we have knocked out a multi-winner cricket football, but there are 4 people who prefer prefer, so just to clarify the notation, there are 4 people who prefer dinner over concert over coffee, three people that prefer coffee over concert over dinner, and 2 people that prefer concert over coffee over dinner. Yeah? What would be the plurality outcome? Even if you haven't seen plurality explicitly, you probably guess what's a natural choice of winner here intuitively. What would everybody want to do? Okay, concert is interesting. Why concert? Anybody who thinks maybe not concert, maybe something else?
Nobody's third choice.
Nobody's third choice. Okay, concert is nobody's third choice. That's an excellent justification. But if we, okay, so are there ways of justifying other alternatives? So, but I mean, the example is constructed with the hope of demonstrating that you can look at each of the 3 alternatives and come up with a rational argument for why that should come out on top, and that's what makes this business kind of interesting. So the plurality voting rule basically says, forget about the ranking, which is a bit of a pity to begin with, but we say forget about the ranking, let's just look at what's going on at the top spot, which is, just imagine that these preferences are intense and you really want your favorite, and the other stuff is, maybe you put them there because you were asked to submit a ranking, but you really don't care for anything apart from your favorite option. Indeed, in many elections, all you are asked to submit is the choice of your favorite alternative, and you're not even asked to submit a full ranking. So this would be a rule that would be relevant in scenarios like that. Given this picture, what would be a natural outcome? Yeah, we go for dinner because that seems to have the most people that prefer it, so that's plurality. In a certain sense, it's a natural choice. Let's just go back to the full ranking. In a certain sense, going out to dinner is also a fairly horrible choice because everybody else hates it, right? It's their least favorite option, and you could construct more dramatic examples to show that the plurality outcome is both in some sense, both the most popular but also the least popular choice. So this is already one problem. A slightly more subtle problem is something that we're about to see. Just coming back to this issue of manipulation. So we say that an instance can be manipulated by a voter or a group of voters if they can agree to not submit their truthful preferences and influence the outcome in a way that favors them, which is to say that with respect to their true preferences, the outcome was X, and with respect to their modified preferences, the outcome is Y, and Y was ranked above X with respect to everybody's true preferences, at least everybody that was involved in the confusion. So in plurality, I'm just going to take 30 seconds to ask if you could see this potentially happening in this instance. So the plurality winner right now is dinner, and as we agreed, 5 out of the 9 people really don't want to go out to dinner. Is there something that they can do to influence the outcome by simply lying about their preferences? So the moment I'm going with forcing an outcome that's anything other than going out to dinner, that's how that would work. Okay, so we can maybe swap the guitar out of the coffee. In the second group of people, these 3 folks here, I need to swap the guitar out of the coffee in some preference. And now if you look at the plurality outcome, it's updated to concert. And as we said, anything's better than dinner as far as these 7 people are concerned. So this is a successful collision. It's not, it's probably not an obvious problem when you first look at plurality, but it's definitely a problem. And you could puzzle yourself about coming up with efficient algorithms to figure out if you can perform a successful manipulation. Okay? But this is an issue which forces us to look beyond plurality, which may have been at the outset the most natural sort of mechanism for determining a winner. This is I'm using quotation from Borda, who came up with not plurality, but sort of extended plurality voting rule, and you can look at Borda, interest of time, I'm not going to describe the voting rule, which is very natural and very popular rule, and he was aware of the manipulation issue, and he sort of, I don't know if he brushed it aside by saying this, but it's just for lack of better alternatives. Yes, so it's just assuming honesty, which is a tricky terrain to get into. So we will not be assuming honesty, but we'll see if there are other ways of breaking around the manipulation issue later in the talk. But for now, let's just move on to another example, which is the single transferable vote. Here, this is more of a knockout, which probably encountered before. So the idea is that you, the voters that are the least popular options on the top ballot. So you look at the, you again give a plurality sort of perspective, but look at the least popular option on the top preference and knock it out. And then the votes transfer in the sense that you adjust the remaining preferences. And then in this case, as you can see, a cup of coffee is what emerges as the SCB winner. Again, this is just sort of to emphasize that slightly different mechanisms can lead to very different outcomes. And hopefully that underlines why this is a very interesting sort of scenarios that can be created. The notion of a Condorcet winner is to look at how people are doing in pairwise elections. So let's look at, for instance, how is concert doing versus dinner? So we only project the entire election onto these guys here, and we look at how many people prefer dinner over concert and how many prefer concert over dinner. So if you've seen the majority graph earlier in this meeting, then this has a similar flavor. So in this case, concert wins over dinner, agreed. So there are 5 versus 4 that prefer concert over dinner, and similarly, if we were to focus on concert versus coffee, again, concert wins because this 6-3. Therefore, so if there is an alternative that beats everybody in pairwise elections, then he or she is crowned the Condorcet winner. And so notice that we've seen 3 different mechanisms leading to 3 different outcomes, all of which seem reasonable in their own ways. So the issue of how do you choose a winner is hopefully starting to feel not completely trivial. What's the issue with the Condorcet voting rule, however? That's right. So you may come up with sort of a null answer because you could hook up scenarios and notice that the numbers have shifted slightly here. And if you work through it, you will see that nobody is a Condorcet winner because the pairwise elections are stacked up in sort of a cycle. This is what it looks like. So when you look at the popular vote, you end up this construct here is called a Condorcet cycle, and you may not therefore ever end up with a Condorcet winner. This motivates the Dodson voting rule, which says that the Dodson score of a candidate is the smallest number of swaps that you need to make a candidate a Condorcet winner, and the chap who needs the fewest swaps to be elevated to Condorcet status is the guy who wins the election. So that's one sort of voting rule building on the Condorcet idea. The main issue with Dodson is probably not terribly obvious, but the issue of finding a Dodson winner computationally turns out to be intractable. So this is our main concern with Dodson. It's a very natural voting rule, but it's hard to find Dodson winners. So that's of course that leaves open the issue of whether you can in some sense approximate Dodson winners, or there are special scenarios when you can do this well. But that's an issue we won't be getting into. Yeah.
So you have to be necessary to do an NISER, or?
Yeah, I mean the adjacent swaps, yes. The number of adjacent swaps that you need to make somebody a Condorcet winner. So essentially, how far away are you from being a Condorcet? Yeah. So even figuring this out for one candidate is not easy. So that's kind of the issue. Let's look at an example of preference aggregation. So because we may be seeing a little bit more of this in the next talk. If you have a bunch of rankings and you want to output a ranking, one way to evaluate the goodness of this ranking is to simply count how much it disagrees with each of the individual rankings, right? And sort of sum up the disagreements or the agreements. So you may want to minimize the disagreement or maximize the agreement. So what do I mean by, so there are many ways of comparing to rankings. There are many well-studied distances between permutations. For chemistry, I think what is used is the so-called Kendall-Tau distance, which is you go through the list of all possible pairs of alternatives, and if both the permutations rank a pair the same way, then that's good. If they rank in different ways, so if the output ranking prefers A to B, but the voter prefers B to A, then that contributes 1 to the disagreement, or 1 to the Kendall-Tau score. So that's how you build up the chemistry score of a ranking. And again, you're looking for a ranking which has the smallest chemistry score. This has a sort of the closest string sort of a flavor, if you like. You're trying to find, okay, so yeah, I mean, I think I shouldn't push that analogy too much. It also depends on whether you're summing the disagreements or looking at the maximum disagreement. That leads you to slightly different situations. But so what I've said here is sum of pairwise agreements, but I think the more common definition of the literature is the sum of pairwise disagreements, which you are looking to minimize. In this case, you're looking to maximize. So, we also define Chamberlin-Courant, which will be, which you might remember was also in the title of the talk, so we will be revisiting this a couple of times. So, Chamberlin-Courant is an example of a multi-variable machine. So you're trying to output a committee, okay? And again, it has a similar flavor to chemistry. You're trying to see how happy are people with the committee that's chosen. So for instance, let's say we have 2 days to do the hanging out business. We do coffee and concert. If I just look at, well, how many people does this satisfy? These 2 outings put together, how many people are completely satisfied? That's 4 out of the 6 people here, right? Because 4 out of 6 people got to do their favorite thing to do on at least one of the 2 days, right? And the 2 people who are kind of still feeling left out. So these guys have, I mean, in some sense are not completely satisfied, but if you expand this scope a little bit and sort of nudge them into being a little more sort of flexible or tolerant, you'll see that they at least get to go to the concert, which is their second favorite thing to do. So in that sense, the Chamberlin-Courant score of this particular choice of things to do on 2 days would be 2. So these guys have no dissatisfaction because they got to do something that they really like, and these guys are dissatisfied 1 point each, if that's how you want to put it. So again, there are more sophisticated ways of calculating the dissatisfaction, but we'll just say if the best option that you got from the committee is ranked 5th, then in your ranking, then your dissatisfaction is perhaps 4, because the top option would give you a dissatisfaction of 0 and just grows by 1 point as you go along. So, but as I said, people look at more interesting dissatisfaction measures as well. But the Chamberlin-Courant score of the committee is again, so you could do max or you could do sum. When we did chemistry, we did sum over disagreements. And in this case, I'm doing a max. But you could actually define this also as the sum. It just gives you 2 variations of the same rule. But I will stick to max because that's what I'm going to be talking about later. Okay? So let's just make this a little more precise because we'll come back to it and make sure that the definition is sound. So let's say that this is the committee that we pick. I want to talk about what's the CC score of this committee. Let's imagine assigning to each voter a member of the committee. So in particular, let's say this was the ranking of this voter. So I'm going to assign to this voter the orange option because that's his best ranked option among all the members of the committee. So his CC dissatisfaction at this point is 2 units. So this would have been 0 dissatisfaction, 1 and 2. So that's where we are at with this voter. And then you basically look at every voter and look at the worst case dissatisfaction, and that's the CC score of the entire committee. So is the notion of what is the dissatisfaction of a voter with respect to a committee, is that sort of clear? Yeah. Okay. All right. So moving on. Okay, so the notion of single peak and single crossing preferences. These are, as I said, switching out to restricted domains. part, we've been just saying, but we get a bunch of rankings as input. Okay? The idea of restricted domains is to say that this is not just a completely arbitrary collection of permutations, but this collection of permutations is some additional structure, which is hopefully motivated by situations that we encounter in real life instances. So in particular, for instance, the way to remember the single peaked definition is to, one of the easiest definitions, one of the easiest mnemonics, if you like, is to think of it as preferences that emerge from opinions over a political spectrum. So imagine that these are candidates that are placed according to whether they're left-leaning or right-leaning or somewhere in the middle. Okay, so you have the extremes there and people who are somewhere in the middle. And chances are that most people have a philosophy that lands somewhere on the spectrum. And you would imagine that candidates who are further away from where your opinion lies are less and less preferred by you. Right? So it's sort of a monotone decay in how much you prefer candidates based on how far away they are from your core preference. So there is a notion of a peak, which is the candidate or the option that most closely resembles your opinion or philosophy, right? So that's your top candidate, your top choice, and everyone else is the further away you are from the peak, the less liked you are by the voter. But that still leaves some room for flexibility, because all I'm saying now is that between C and D, I know for sure that C is less preferred than D because C is further away from the peak than D is. Between F and G, I know for sure that G is less preferred than F because G is further away from the peak than F is. But between, for instance, B and G, I'm not sure. There is still flexibility on how you interleave these two rankings. Yeah? So that's why even for a fixed choice of a peak, you could actually spew out multiple rankings, which are single peaked with peak E. Little more, so this is the typical visual that goes alongside single peak preferences. As I said, preferences decay from the peak and then they can be interleaved any way you like. Slightly more formal definition is that if a preference claims to be single peaked with respect to this ordering, so you have a baseline ordering always. If a preference claims to be single peaked with respect to that order, and in this preference, if you have that X is preferred over Y, then one of these things must be true. Either X is itself the peak, in which case it's preferred over every other candidate, so no problems there. Or X and Y are on opposite sides of the peak, in which case there is no constraint on how you rank them. But if X and Y are on the same side of the peak, so X is not the peak, and X and Y are on the same side of the peak, then Y better be further away from the peak than X is. Yeah? Is that fine? Is that reasonable? So these are single peak preferences, and as I said, there are evidences from actual real world data as to why this is a reasonable restriction to look at. There's also other motivation. If your preferences are single peaked, you never encounter a Condorcet cycle. If your preferences are single peaked, as far as picking the Condorcet winner is concerned, and if the mechanism that you designed is picks the Condorcet winner, which is guaranteed to exist, then there is really no incentive for manipulation. Whether a bunch of preferences are single peaked or not can also be checked for in polynomial time. And as I was saying earlier, it's considered widely by many to be a reasonable model of real world sort of instances. So I was going to get into an explanation for why there are no Condorcet cycles and why there is no room for manipulation, but in the interest of time, I think I'm going to skip through this. I'll quickly, however, show you why you can do Chamberlin-Courant easily for a single peak. So I think I forgot to mention this, but Chamberlin-Courant is also right up there with Dodson and Kemeny in terms of being hard to compute. So if you wanted the optimal Chamberlin-Courant preference, the optimal CC committee, that's not easy to find. Maybe the intuition is already here, which is that so let's look at the decision version of the question, which is to say that I'm looking for a CC committee with a score of at most k, which means that I'm looking for, okay, let's say a committee of size k with a score of at most c. Okay, so that means I get to pick k people, and every voter must have a representation, meaning must have one of these k people within its top c positions. That's what it means to have a CC committee with score c. Right? So that hopefully conveys a sort of hitting setish flavor, right? Because you can really think of the top c positions for every voter. Think of that as a set, and what you're trying to do is you're trying to pick all these sets with k candidates. Right? So hopefully that conveys why CC is hard. But if your preferences are single peak, then there's like this fun algorithm which is actually quite straightforward. So let's see. Yeah.
So, is it easy to check the committee in the
so, given a committee, you just assign to every voter the best. Okay, is it the best CC committee? Is somebody asking that? I'm not completely sure actually, that's a good question. Like, do you know if a given committee is the optimal CC committee? Off the top of my head, I think there's no obvious certificate, but maybe, yeah, think about that a little more offline. Yeah. Checking if it has a particular score is easy. Checking if it's the best amounts to providing evidence that there is nothing that is better. That's not obvious to me. Okay, so if you look at the voters, which I now promise to have single peak preferences, and let's assume that you have recognized that they're single peak, so you have the underlying single peak ordering. Let's just look at where the peaks are for these voters, so maybe they're here. Suppose you were looking for a CC committee with score 0, which is to say 0 dissatisfaction. Everybody gets their top pick. How many, so there are 4 voters. How many candidates would we need to pick in the CC committee? I'm not fixing the size. Hopefully it's clear that we will need to pick all the 3 peaks, right? So you will need to pick E and B and D. They're all forced because I have demanded that I want a CC committee with score 0. So you have to basically pick everybody who occupies the top spot, and single peak preferences. The peaks essentially tell you where the top spot candidates are. Okay, so you would have to essentially pick all 3. If there were 4 distinct peaks, you would have to pick 4. If they were all in one column, but that one candidate would do it. Instead, let's say I'm looking for a CC committee with a dissatisfaction of 3, meaning I'm willing to go out to the 4th position in these individual rankings. Yes? So in that case, I would have to look at, for every voter, I would have to go and ask him or her, what are your top 4 options, right? And from every voter, I figure out what their top 4 options are. Is there any intuition for what their top 4 options would look like in this picture? Would they be all over the place, or would they be a little more constrained? Given that the preferences are single peak, and given that the peaks are at the red dots. So so let's look at the first voter. His top preference is right here. His second best preference, can it be this one? No. There are only 2 options for his second best preference, which are right, either side of the peak. So it could either be D or F, but it cannot be anything else, because if something else, you violate single peakness, right? Because if the second position was C, then where do you place D? You're going to place D after the second spot, which means you violate the single peak property, right? Which means that if you go out further from the peak or the top spot into the next 4, 5, 6, how many ever positions, they're all going to occupy. So I don't know how far out they're going to go on either side, but they're definitely going to be a contiguous interval. Yeah. Going to form contiguous intervals around the peaks, and now you want to really stack these intervals using k-lines. That's what the CC committee is. You want to make sure that you don't miss, so you pick candidates so that you don't miss any intervals. So in fact here, You even have committees of size 1, and then 2 committees of size 1 that will do the trick, right? So essentially, Chamberlin computing a nice Chamberlin-Courant committee on single peak references boils down to stabbing intervals, which can be done quite easily. Okay, let me also quickly touch upon single crossing preferences. And so this also can be motivated, but I'll skip the story. A profile is single crossing if this holds for every pair of candidates that the voters that prefer A over B come before the voters that prefer B over A. I should have mentioned that there is an ordering of the voters for which this happens. So in single peak, we were lining up the candidates. In single crossing, we are now lining up the voters. Okay? And so the picture could look like this. So project the election on any pair of candidates. It should be the case that for a while the wind is blowing in this direction and then it switches, but then it never switches back, so there's no turning back once this happens. So it's only one point of view. That's what is called a single crossing preference. They should have every pair of voters, and it's a similar storyline as with the narratives that we have for single peak preferences. There are no policy cycles. These profiles can be recognized and followed up as line, and hopefully a reasonable model of that. So let's briefly touch upon how you can do Chamberlin-Courant for single crossing preferences efficiently. So let's recall that this is how we define the notion of dissatisfaction. Now the claim is that on single crossing profiles, an optimal CC committee actually has something called a contiguous blocks property, which I'm going to define in a minute. Imagine, so the voters are lined up in the single crossing order, because that's an order I have, so why not use it? So imagine that the voters are lined up in the single crossing order, which means, let us recall that what that means is that for any pair of candidates, right, there is a point up to which one candidate is preferred over the other by all the voters up to this point, and after this point there is a switch and the preference goes the other way. The switch is not mandatory, but if it happens, it can happen only once. Okay, so that's what we had with the notion of single crossing preferences. Now imagine that somebody gives you a CC committee, okay, and with each voter you have kind of labeled the voter with his favorite option from that committee, as we did here. I'm not going to go back to the slide that defines CC, but you remember what we did. We said that given the voters' ranking of the candidates and given a committee, I'm going to assign to this voter his favorite person from the committee, his highest ranked candidate that is in the committee. So those are the labels here. So for this voter here, the green candidate turns out to be his top ranked candidate among all the candidates in the committee. I want to argue that this sort of a scenario cannot happen if the profile was single crossing with this single crossing order. Is that a reasonable thing to say that this cannot happen? So for this voter, the green candidate is his favorite. For this voter, it's the yellow candidate, and then for this voter, it's again the green candidate. What does that signify? Okay, I'm going to parse the muttering as two crossings, so it leads to two crossings, right? So because this implies that this voter prefers green over yellow, because by the very definition of this allocation. Similarly, this would mean that this voter prefers the yellow candidate over the green candidate. And here, green is preferred over yellow again, which means that we have two switches, but single crossing profiles commit to only one switch. So that's a contradiction. So if you look at these allocations, you get like this very neat what is called the contiguous blocks property in the literature, which just means is that the assignment of one candidate forms a continuous interval over the voters, if you look at how these allocations happen. So you don't mix them up like that. Which gives you a pivot to write a bit of a DP, so let's just define the DP table. So I've not made the range is explicit, but hopefully it's clear. So APQP denotes the best committee of size T that you can choose from among the first P candidates and the first Q voters. So you project the election on the first three candidates and the first few voters, and you ask for a committee of size D, and what you store is the best possible score that you can achieve, right? So, so this is just to highlight that T is the size of the committee. We're looking at the first three candidates and the first three voters, right? So this is what we have. As we often do with most dynamic programming algorithms, we are going to try and pivot on one of the extremities. I'm going to pivot on the last candidate. And we're going to go into two universes like we were doing for every FBS talk. So what are the two natural universes here? Let's call this candidate CP. What are the two natural cases that arise? Either the candidate CP belongs to the optimal CC committee that I'm looking for, or the candidate CP does not belong to the optimal CC committee that I'm looking for. In the case that CQ does not belong to the optimal committee, then it is easy. I just go back to the first P minus 1 candidates, look for a committee of the same size because CQ isn't even occupying the spot. And I'm still looking at the first P voters because nobody has been allocated a candidate yet. Yeah, is this reasonable? Yeah, okay, everyone with me. The second option is when CQ does belong to the optimal solution, and this is where the contiguous blocks property comes in handy. So what would you wager happens if CQ does belong to the best CC committee that the committee that we're looking for? In this case, what happens is that CQ gets assigned to a bunch of people, and we know that that's going to be like a contiguous block of people. We just don't know the length of that block, right? We don't know how many people CQ gets assigned to, but we do know that it's going to get assigned to a bunch of people here and nowhere else, so we can forget about them once we have figured out the size of the block. Yeah. What do we normally do in DB when we don't know something? We can guess, yes, thank you. So we just guess the size of the block, which I'm saying is X, and we're going to try all possible choices of X here, all possible choices that are reasonable. So I haven't made the indices explicit, just to keep the, because I didn't have enough space, but hopefully it's clear. So you want to guess across all possible choices for X, and then we take a win over all the possibilities that we're looking at. So that's essentially what we do. This appeared a while ago, probably have the citation a couple of slides back. Okay, very quickly in the last couple of minutes, the idea of single peak and single crossing domains have seen much success, and for good reason. Hopefully I've made a convincing sales pitch, but the business about being reasonable representation of real-life instances was always accompanied with a question mark on the slide, so I'm just going to address that briefly, just to say that real-life instances are probably not going to be as cut and dried as we just described them to be combinatorially. So a lot of people have been looking at ways of generalizing these notions in natural ways to account for the noise that you might see in the real world. So for instance, people have gone beyond working on a path to more complex structures like trees and circles and even general graphs. So we'll actually talk about that more. I'm not going to get into it. There are notions of single peak and single crossing width where you allow for bundling up the candidates. All of these notions generalize what we've already seen. So you're accounting for more and more varied profiles. So here, very roughly speaking, you allow for bundling up candidates and looking at them in unison, and you allow for the boxes to be messy. Realize it's a totally vague way of saying it, but you can look it up if you like single peak width and single crossing width. You could also say that, well, maybe I can achieve, maybe the profile is just K voters or K candidates away from being structured. So maybe if I delete a little bit here and delete a little bit there, I recover something that's nice. And this has been looked at from both an approximation and an FPD perspective. What's the smallest amount of noise that you need to get rid of to make your profile look nice? And this is something that we followed up on a bit. So given that we can actually recognize these deletions in a reasonable way, we generalized the CC algorithms that we just saw earlier and a few others. so that they work on these noisy profiles. And so you get sort of FPT algorithms in FPT parameterized by the noise to obtain optimal CC committees on profiles that are close to being single peak and single crossing in the sense of candidate and photo deletion. So, okay, so there's some detail there which I'm going to sort of avoid. If you want to propose your own domain, which I'm going to suggest that you do later, just make sure to think about whether the domain can be recognized efficiently and whether it serves, whether it has an algorithmic sales switch to go with it, and if it preserves some nice axiomatic properties like having, for say, winners and things like that. So I'm just going to quickly wrap up here. One thing to watch out for is that single peak and single crossing preferences are almost too nice because all the bad stuff that happens, like manipulation and bribery and things that you don't want to happen, they also start admitting efficient algorithms on these restricted preferences. So it's just a heads up, it's a red flag to watch out for. But essentially, I think the really nice thing here is to parameterize by distance to nice things, which is something that's being done a lot in the graphs world and could probably be explored here. And I'm practically done. So yeah, all right. So as I said, come up with your own domain restrictions if you like, and maybe look at the impact of these domain restrictions in places other than voting. I'm sorry about running